All right. Hey, everyone. Welcome to week 4 of Beginner Track. Glad to have you back again. This week we'll be going over logistic regressions and multi-class classifications, two pretty natural extensions of what we learned last week, which is linear regression. Again, feedback forms in the chat as well as on the slides, so please fill it out. If you're following along on the ACM membership portal, the attendance code for today is Nigeria. And again, there's actually a really cool pattern between all 7, like a really cool pattern between all 7 of these attendance codes. And I guess it's it's week 4 of this, so I'll give you guys a hint that all of these attendance codes are countries, which you guessed, which you probably understood, and they're also actually related to sports. So that's a hint. Think about it, and maybe you can guess a relationship between them, like in the coming weeks. Yeah, only I know what it is. I don't even think I told Jensen. So yeah. All right. And again, Discord's right here as well. Every Monday we host office hours. So if you have any questions or want to talk to us about machine learning, just show up on Mondays on the Discord, and we'll be happy to answer your questions. I'll talk to you. All right, let's get started. So first thing, really quick recap about linear regression. It's pretty important to start off with for this week's stuff. So the main thing with linear regression is that our goal is to basically find a line, or like the coefficients as well as like the bias or the intercept, so that our equation for that line fits the data the best. Basically, it has the least error to all those points. So with that line, we can now predict the output of like other inputs. Like for example, from last week, we had a random data set, and if we had been given a new data point, we could have used our linear regression to figure out, given some certain x input, what's our y output, kind of thing. I guess a quick question for you guys to just briefly remember what these two terms are up here. Is linear regression a classification or a regression? The name might give it away. But yeah, write it in chat, or if you want, you can say it out loud as well. But yeah, and hopefully it makes sense which one is which. I'll go over it in a second too. But yeah, okay. So I got 2 regressions in the chat, and yeah, I agree. So yeah, quick recap of what those 2 terms are. Classification basically means that given some data, we're going to say like our output is either going to be like class 1 or class 2 or class 3. So like if we're given a bunch of data, like is our output like chocolate ice cream or vanilla ice cream or like strawberry ice cream? Like that's classification. Meanwhile, regression is more like taking a bunch of inputs, the same inputs, but turning that into a continuous number. So basically, that can mean like, let's say you want to figure out how long your ice cream will melt based on some how long your ice cream, or how long it'll take for your ice cream to melt, given some factors. That would be a regression, because our output would be the number that would tell us how long in minutes or seconds it would take us to it would take the ice cream to melt. So that's the main difference. So yeah, in this case, linear regression is a regression, and in this case, the names match up. So it's a regression because we're basically taking like an x input or something, or some set of inputs, and mapping that to an output, which is continuous. So like there's no like discrete outputs. So there's like no like bin 1, bin 2, bin 3. It's just like any number from like infinity to infinity, negative infinity to infinity. All right, with that in mind, let's keep moving on to the formula for linear regression, or the hypothesis function. So up top, right, we have our hypothesis function. So it basically says that given a certain x input, where our x input is actually just n-dimensional vector, x1, x2, x3. Actually, who remembers what each of these x1, xi's are? Like, what do they stand for? Actually, they're here. But, I'll ask anyways, see if you guys remember, and also so you guys can read the slides. What does each x1, what does each xi represent? an input. Yeah, it does represent an input. I'm looking for a term. I'm looking for like a certain term in particular for each one, because like this whole thing is an input. I got each individual parts. Yeah, exactly. Eva got it's a feature. So each of these x's are features. So like for example, if we were predicting house price, for example, or like a house price, just x1 could be the number of bedrooms, and x2 could be the number of bathrooms, and x onwards. So each of these terms is like represents something about the situation or object. So it's a feature. And so as you can see above in our actual equation, our prediction is going to be each of our features multiplied by a certain weight plus a bias term. So like that weight 1 times x1 plus weight 2 times x2 all the way on plus a b term. And so again, our weight is also an n-dimensional vector because we're going to be like multiplying w1 by n1 x1, so same dimensions. And our b is actually a real number because x1 and w1 themselves are real numbers, so the product is also a real number. So this whole thing on the right, like from all the weights and biases or the weights and inputs multiplied, is a real number. So b is also a real number. So that's our hypothesis function. That's what we're going to use to figure out, or that's what we're going to use to make our best prediction. And so in order to like hone our prediction, we need to have a loss function. And so again, our loss function, like we talked about last week, is tells us how bad our model is, basically, like how erroneous it is. And so in this case, we have y hat I, which is basically our model's output. So like given some certain inputs, that's our model's output. We have y sub I, which is the actual value of the data. So like the house actually cost like $500,000, but like our prediction was $600,000, for example. So those are those two things. And the every I basically means which training example order. So if we had like 100 houses, we go from 1 to 100 on all these houses. And then we'd average it over number of data points we have. So if you have 100 data points, we're going to sum all 100 errors, square them, and then divide by 100. So this is why it's called mean squared error, because we're squaring the error and then we're taking the mean of that. So yeah. And then one of the other important things we talked about was gradient descent. So this is how we figured out, given our loss function, how to update our weights to become even better, or how to update our weights to like go towards a better, like the best prediction possible. And so we ended up with these two formulas from last week. Jensen actually like wrote out the proofs for them as well, which is pretty cool. But these are our formulas for figuring out our partial derivatives for each weight. So the derivative of the loss function with respect to each weight is this jumble right here. And to update our actual weights, we take our existing weights and subtract our partial derivative times a certain alpha. And the reason why we do this is because taking this slope, taking this away from it, will actually get us that will actually get us closer to minimizing the loss as fast as possible. Same thing for bias, and yeah. Hopefully it's all look familiar to you guys, because we talked about this last week. But if it doesn't, feel free to ask any questions about anything. Okay. All right. So with that all said, let's do a quick poll about linear regression and see if you guys understand or have a good grasp of what it is. So let me launch a poll real quick. All right, poll is active. And the question is, what is linear regression well suited for? Like which of these tasks? Is it determining whether an image is a dog or a cat? Predicting whether a tumor is benign or harmful? C, creating theory, definitely correct. Or D, predicting MCAT scores based on college GPA. Wow, you guys already answered before I have said the full question. So I think you guys got this. You guys got this down. So yeah, 100% success rate. Oh, I'll say it here, you guys. 100% success rate. Great job. So yeah. A quick overview of why. I'm sure you guys already noticed, but let's just go over it real quick. Creating theory is just like too complicated for linear regression. To be brutally honest, it's just a bit too complicated for linear regression. We talked about it week 1 actually, about like voice recognition as well as speech to text and things like that, or text to speech and stuff. So that's more serious stuff. And then the first two are actually not regression tasks. They're actually classification tasks. So is it a dog or a cat? Is it not like a continuous number? It's like is it in bin 1 or bin 2? And same for benign or harmful. Is it bin 1 or bin 2? So those are not linear regression examples. But they are the topic of today, which is logistic regression. So let's get into the motivation behind logistic regression real quick. So at the moment in our toolkit, we have linear regression, which is used to predict continuous data. So for example, we have house price, but we also want to do classification as well, because that's pretty important tasks. So we have logistic regression, which is basically used to say, is our data point or is our set of features and data, is that like in class 1 or class 2 or like class 3? We also have KNNs, yeah, that's true. But KNNs, as you noted earlier, KNNs don't actually have any learnable parameters. So as a result, you want to have a model that can work on bigger data sets, which KNNs can't always do. And so just to see that in motion, we have up top a linear regression might predict a number, like well, it has to predict a number, which is $250,000 for this house. I think it's pretty cheap actually, for considering how big this house looks. But that aside the point, the fact is that this is a number and it's a continuous number. So it can go from like negative, it can go from like 0 to like as long as you want. So it's continuous. On the other hand, we have our cat picture right here. It's a pretty angry cat, but our cat picture right here is classified as a cat, which is not a number. It's actually just like a cat or a dog or some animal. So there's finite discrete options for this. So that's the big difference. And so our goal is to figure out how we can create some model that can classify data instead of always predict continuous data. And so a quick example for this is, let's say we wanted to predict if it's going to rain today or not. And so the obvious question, which we asked last time too, but we want to ask again this time, is what kinds of features would we want to look at? So like when you go outside, what do you all look for to figure out, is it going to rain today or not? Clouds, definitely a good choice. Humidity. Might be hard to detect yourself, but definitely with some measurements as well. So if it's really humid, you could feel it too. So definitely too. Anything else? If it has been raining in the past, yeah, definitely. There's definitely like cycles and like storm systems and stuff that makes sense. Yeah, those are all great examples. And so again, we're going to focus on features and make sure that we can take in input as features as input to feed our model. And so, the way we're going to like actually, given our features, we're going to actually pass them into a function or model called logistic regression. And with that, we can classify a day as either raining or not raining. And so let's say we use some data, like let's say we have like our location, our temperature, our cloud cover, so how many clouds we have, our humidity, and wind speed. And so given this scenario, like us intuitively, we can kind of see that like it's probably not going to rain today. Like 105 degrees, like rain's already kind of unlikely. Like having low cloud cover, even less likely. Los Angeles, even less likely. And like all those factors add up and add up. So the fact that we're going to predict that it's not going to rain today. And so this is an example of how we might use our features as inputs to get an output, which is like how we do it in our brains at least. But the important distinction to make here is that we're not going to say, is it going to rain or is it not going to rain? We're going to say, is it more likely to rain or not rain? We're going to say, like, which one do we think is more likely to happen? So it's more of a probability question rather than a yes or no question. And so just to have some like examples in our head before we dive into the model itself. Some examples include tumors. So we had this example earlier, but there's some really awesome models out there right now that can classify tumors for doctors, because it's not always obvious to them if a tumor is benign or malignant. And actually working together with doctors, these models are actually even more accurate together and like separate individually. So that's even better. Another really famous case is numerical digits. So like if someone writes a number on a paper, is that a 1 or a 2 or a 3? And so this is an example. There's actually a really famous data set called MNIST, which is basically a bunch of handwritten numbers or digits, and which can be used to predict numbers. And so now that we have those examples in mind, let's talk about what exactly the input and output is. We have our features. We need to make that into an actual input. And we also need to figure out, once that goes through the model, what are we going to output? And what does that mean really? So let's say we're working on an image classification task. So in that case, our array of pixels is our feature. So if we have a picture of like a cat, each of those pixels and and each of the pixels in the whole picture, which is going to be a 2D array because 2 dimensions of a picture. Each of those pixels will be an input. And so yeah, each pixel is therefore a feature of our method. And then as an output, this might be surprising to you guys, but our output depends on actually how many classes we have, right? It follows a pattern, I would say. So let's say we're going to go for a binary classification, meaning we're going to have 2 classes. In that case, our output's either going to be a 0 or a 1 or anything in between. So we would in theory, we would want our output to either say 0 for class 0 or 1 for class 1. So for example, we might have like 0 be cat and 1 be a dog, or like 0 be hot dog and 1 be not hot dog, for example. And so yeah, funny example. Yeah. And hopefully we get for this case that like this would be a 0 on the left. And this should not be this should be a 1. So yeah. And while our model, when we get to it, won't actually return an actual 0 or a 1, we can still figure out from our model's output if it's closer to 0 or closer to 1 is the most important. So that brings us to the actual model itself, logistic regression. Before I go into that, any questions about the motivation or like the examples? Eight recipes for octopus. Interesting. Not quite sure what that means, but I'm probably missing a reference, honestly. Or a popular AI thing. I don't know. My bad, though. Or is it supposed to be about this? I don't know. Anyways, if it's important or if I makes sense, if I'm like not cultured or something, just let me know later. Anyways, we'll get into logistic regression now. I don't think there's any huge questions. So logistic regression. So I'll try to build off of our old function for linear regression and make that like a function for classification. So we want our hypothesis function, instead of outputting a number like anywhere from like -infinity to infinity, we want it to input a probability. So that means it's got to be between 0 and 1. And so currently, like I said earlier, our function has the entire real numbers as its output. And so the question becomes, is there a way to map this function, a linear regression function, to a certain output space between 0 and 1? And so that is the question for logistic regression to figure out. And so there actually is a way. I went a bit quickly, but you guys saw it. It's called the sigmoid function. And so it's pretty awesome. And as you guys can see on the right, it has a really cool property where it's bounded between 0 and 1, which is exactly what we want. So if we apply the sigmoid to the output of our linear regression right here, our output will guaranteed be between 0 and 1, which is a probability. So that's great. And so the function itself is actually 1 over 1 plus e to the negative x. And it's pretty important against in like general machine learning. So it's important to keep in mind. And so the important traits I'd notice are that like even starting at low positive, but actually more prevalent at high positive numbers. Like anything like beyond like really positive is like basically one, like doesn't reach one, but it's like basically one. And anything really negative is basically reaches 0. And in between, it starts to get a little bit more like in between zone. But the important things that we know that 0.5 actually occurs about at 0. So this is basically our cutoff point for classification. And so, yeah, quick thing, so that if sigma of 0.5 or sigma of x is less than 0.5, that means, or x is negative basically. So as you guys can see, everything left of this 0 line has the output of less than 0.5. Everything right of this output has an output greater than 0.5. All right, and so 2 questions for you guys are, is the output of the sigmoid, is that continuous? I'll start with that. Is the output continuous or not? Yes. Anyone else have a similar or different idea from Maxwell? Yes, 2 yeses. All right, I'll take 2 yeses as like almost majority at this point, because it's pretty big majority actually. So yeah, you guys are right. This is a continuous function. So it's actually defined for any x, so any real x. So like even negative like 999 works here. It'd just be a really negative, it'd be a really value close to 0 basically. So this is continuous. So the question becomes, if this is continuous, how do we use that to classify things? Like, doesn't that defeat the point of classification? Because continuous basically means it's a regression. So how do you guys think, or how does everyone think we can use this function to classify things? Okay. Yeah. So Maxwell says if it's greater than 0, if x is greater than 0, then it's 1. And if x is less than 0, then 0. So yeah, basically it's pretty similar to what I would say. I guess the important distinction is that like even if like you probably want to use sigma in this case, because the sigma function is actually what we're going to be using. But basically, if the sigmoid output is less than 0.5 and it's the then for class 0 and it's greater than 0.5, we're going to go class 1. And so that's like the general idea behind it. So Julian says compare probabilities from 0 to 1 of different possible classifications. I guess, yeah, in actuality, yes, because it's like we're going to actually like get the value of the output. Like, so like say, for example, let's say our input to the sigmoid function was like -1 or something, then the output would be like -0.25 or something like that. I don't know exactly what this is. Whatever this is, it's less than 0.5, so we're going to set it to 1 class. So basically, we're going to compare how close the output of a sigmoid is to 0 or 1 and choose the closer class. That's the general idea. So you guys both have this like a similar idea, and they both are essentially correct. So, oh, any questions before that? Because next part is going into the model itself. All right, if not, let's go into that building the model. So this is probably the coolest part of the function thing, but like putting it all together, let's create our hypothesis function. So we have our linear regression, which is our weights times our input plus our bias. So you guys might be confused about how it's visualized here, but imagine this is our weights vector, and this is our bias vector, or our inputs vector. So we're doing basically, we're multiplying the vectors together. And so what that is basically, we're taking, it's basically it's the same multiplication as we see in the hypothesis function, but in vector or matrix form. So that is the weights times input, and we're adding the bias to it, and that's h of x. And so now we're going to apply the sigmoid to that, and so we're going to basically put we're going to set like h of x to be like x in this case. So that's why the input's here, and so now we have our sigmoid function. And then now that's actually our prediction function, our hypothesis. So our hypothesis is basically applying the sigmoid to our linear regression, and that looks like this basically. So instead of having e to the negative x, we're going to actually input our linear function as our x in this case. And so as a result, depending on our weights and our biases, or our only single bias, actually, there's no biases, only our one bias in this case, a certain input x will basically output a value between 0 and 1. And based on if that output is greater than or less than to 0.5, we're going to classify it based on that, basically. So if it's closer to 0, it's going to be a 0. If it's closer to 1, it's going to be a 1. And this works for binary classification because there's only 2 classes. And we'll get to the workaround for having more than 2 classes later, but this is for binary classification for now. And so yeah, quick summaries in the bottom. Less than 0.5 or greater than 0.5. And so now let's dive into how we figure out if it's going to be a certain class or not. And so we can think of the output of our model as being the probability of it being a certain class given our input features. And so that means that, okay, ignore the like notation over here, but this basically means what's the probability that our output class is 1 given our inputs. So like what's the probability of it being 1 given some certain inputs? Oh yeah, it's right there. Cool. Awesome. I jumped the gun a bit, but it's there. All right, so given that, we have our hypothesis function. So using that, what are we like in theory trying to find? So on the right, you guys can see, or everyone can see, some cats and dogs placed on a 2D array or on like a 2D graph. So let's say, like for example, like the y coordinate is like length of whiskers or something. So like dogs have no whiskers, and then like the x coordinate is like, I don't know, amount of tail wagging per second. So yeah, that's the x coordinate. So that dogs have a lot more of that. So that's like the general gist of it. And so given these data points, we can kind of in our heads see like a clear difference between the two groups, and that like the dogs are at the bottom right and the cats are in the top left. And so in more formal terms, that basically means that we need to find the decision boundary. So basically we need to find a certain line such that depending on which side of the line we are on, we're going to classify it as such. So like if we're on the left side of some certain line, it's going to be blue. And if we're on the right side, it's going to be orange, for example. And so in this case, you probably make a line like about here or something. But yeah, that's the general idea. And so in particular, that means we have to figure out some weights and a bias such that given our x, we need to basically figure out if it's on the left or right side, which is basically is it a 0 or a 1. So you could think of the left and right side as being less than 0.5 or greater than 0.5 on the sigmoid function after we sigmoided it. So this is why 0 or 1 is used in this case. And so the question now becomes how do we find these weights and bias? And so again, we have our everyone's favorite math terms and machine learning terms, gradient descent on an epic cost function. So let's go into the cost function. So you might think at first we have MSE, right? MSE is like pretty awesome. It makes sense intuitively. Like just a square error and take the average of that. But there actually is a kind of a problem with MSE on data between 0 and 1, or basically data that isn't the entire plane or like the entire real numbers. And that problem is that, as you guys can see, like if our inputs like last week are like from negative infinity to infinity, the slope gets us to a minimum, right? So for example, like if we start like at this point, like around here, like we're gonna have a gradient or a slope in this case because two dimensional. That's like in this direction, right? And so we're gonna go down the hill basically towards the minimum point of our cost function, which is where we want to go. But our MSE looks a lot different when our outputs are constrained between 0 and 1. And so it looks a lot more like this, which looks a bit like an inverse sigmoid function basically, but not really, but looks kind of like that. And so the big problem here is that, let's say that your current weights and biases get you to about like this point on the loss curve right here. So anyone have any ideas what might happen if you get stuck on this, if your weights get stuck here? This is more of a theoretical question, so just feel free to guess or have maybe any ideas for it here. But like, what happens if if your weights end up here, for example, or like really far positive or negative, for example? Again, this is like more of a, we haven't covered it yet, so this is more like a feel free to guess or have anything you have, like any ideas you have. A quick hint is that think about the slope at like this point compared to like this point. I'll give you guys a bit. I'm prepared to wait for a little bit, so take you guys' time. It can be anything. Even if it's wrong, it doesn't matter. We'll go over it. Max will ask, does it blow up on either side? What exactly do you mean by that? Do you mean like, the loss is really high? Goodness, there's a somewhat high error means a really high MSE. I guess, yeah. I guess, but like, given that a very high MS means somewhat high error, what does that mean to our hopes of making our model better, for example? Go overcorrect? I guess that's interesting. It's a good guess for sure. But actually, surprisingly enough, it's actually the opposite. It'll actually not correct enough. Like, it's kind of surprising, I guess you'd think, but like, it makes more sense if you look at this graph. Don't worry about it. It's like you had the idea down. It's like the reverse on like what happens in the model. So don't worry, you had the right idea. But the general idea is that because we're stuck at this like part of the weight of the loss function, if we take our slope here, it's like almost vertical, right? We're not changing, like if we follow like our alpha times our derivative right here or our gradient right here, we're gonna go like nowhere. And so it's really possible for us to actually get stuck at this like loss of like 0.5, never get down to 0. And so that's the big problem, is that it might get stuck in like decent but like kind of bad territory. So we don't want that. And so that's the reason why we're actually going to incorporate a new loss function this time. And so yeah, thanks Maxwell and Jonah for participating. That was really awesome for you guys. And yeah, don't worry if you got it wrong. But you guys have like great suggestions, so that's what counts. So now that we've just destroyed our hopes and dreams of using MSE, you might be kind of wondering, what are we going to use instead? Like, what's our alternative? And so, all right, next slide, please. This is where our great friend binary cross-entropy loss, kind of a mouthful, but if you want to have a simpler term, BCE loss comes in. And so the way that we get around this weird loss function, like this loss function problem, is that we're going to use this log loss function. And so this is what it is. So given our prediction and our label, we're taking negative of our label times our times log of our prediction minus 1 minus this times log of this. And so this looks confusing, but let's break it down by looking at what happens to it at certain terms, at certain inputs. And so yeah, this is our function. And so again, prediction, label, same thing. We talked about that before. But the important questions are, what happens to y? What happens when y is equal to 1, and what happens when y equals to 0? Y equals 0. And so, I guess this kind of gives it away, because I didn't hide these, and I didn't hide these in the positions. My bad, but it's okay. Let's go through them real quick. So when y, our prediction, or when our label is 1, what we get is that this term stays, because -1 still stays, right? But 1 minus y becomes 0, so this whole term gets canceled out. And so our loss becomes basically the negative log of our predictions. On the other hand, if y is 0, we get the other term instead, which is -1 times 1 minus that. And so what that really means, we'll get into the next slide. But the important point is that this equation basically only has 2 cases, really. It's basically like, is our prediction 1, or is our label 1? Then it's this case. Is our label 0? Then it's this case. So it looks complicated, but the real thing is like these 2 cases, because y can only equal 0 or 1. So that's important to keep in mind. And so again, we can make our loss function. So right now we have our loss function in terms of our prediction and our label. But again, we know that our prediction is actually a function of our weights and biases. So you can substitute, we can make our loss function in terms of our weights and biases again. So we're just going to average it over all of our inputs, and we're going to take that loss function for each one. So remember that remember the prediction, you might not see W and B in here, but that's because W and B are used to make y hat or yi hat or y sub I hat. So that's header here. And so yeah, in full form, it's more like this. And as we know, y sub I hat is like B plus W1 times X sub 1 all the way to X sub n. Yeah. So those are our full equations. Oh, we didn't go into it. Wait, okay. I guess yeah. We'll go actually I think it's the other side. All right. Poll number 2. This is kind of a not a cool poll. It was poll that was there, so I'm using it. But this poll basically asks you, do you remember what we just talked about? So I think you guys got this. Basically, the question is, which of the following functions is the correct loss function? And so I'll launch it for real quick. The choices are A, B, C, and D, because I was like, I did not want to like copy, like write the equations down. So just look at the slides, figure out which one is which, and yeah, take your time for sure, because it's gonna be kind of confusing given like the visual. But if you can remember what happens for y equals 1 and y equals 0, this should be a lot easier. All right, no rush, but I'll give everyone like 15 more seconds. All right, cool. Thanks for answering on time, everyone. All right, so we have a general consensus, and that is that the answer is, general consensus is that answer is B. I think I agree in this case. The main difference between between B and C are negatives. And so if we go back real quick and we can check, because honestly, I think this is right, but I'm not fully sure. Let's go back and check. So yeah, you guys can see it just negatives in this case. And so that's the main difference between these two functions. Is there actually a slide on what the significance is? No, I don't think there is. So because of that, I'm gonna actually go back and just change this real quick. But in case you're wondering why these terms are these terms, basically what we're gonna do, log loss is basically used to like kind of normalize our data, as well as take loss. But the important things are that the main difference is that if it's one, our log if it's like if our true input is one, we're gonna basically take how off it is. So basically we're just taking the log of our loss. And if it's not if it's 0, then we're gonna take 1 minus that. So if you could think about a number between 0 and 1 minus that number is basically like the complement to 1 basically. And so we're figuring out like I guess how close is it to 1, and that's how bad it, like that's the negative of that is how bad it is. That makes sense. Might have confused you guys a bit more, honestly, but hopefully it didn't. If you have any questions about that, feel free to ask. I think it'll make more sense when we go into the next part though. I think that's my part though, so I'll pass it on to Jensen, I think.
All right, yeah.
Yeah, cool.
All right, hopefully everyone can see my screen. So I want to clarify like something that Nikhil said earlier. So like about like why there's a negative sign in front of the terms here. So the main reason is because like y hat here is between 0 and 1 because of the sigmoid function. So when you take the log of something that is between 0 and 1, you get a negative number. So we want our loss function to, I guess, always output a positive number. So that's why we add a negative sign. So hopefully that is clear. Let me know if you have any more questions. I guess if not, I'm gonna move on. Wait, there is a question. All right, cool. All right, so the gradients of I guess binary cross entry looks something like this. So recall that the derivatives are very similar to those for linear regression, but like the only difference here is like these the gradients here are in matrix form. So y hat now is actually a column vector with m rows and 1 columns. And yeah, as usual, y has our predictions, and y is also a column vector with all the targets of our data set. And now x is actually like the data, but it's a m by n matrix. And so I guess the derivation for binary cross entropy is gets pretty ugly. I think I tried to do it yesterday and it gets pretty ugly. So if you want to check out the full derivations, please check out this link. And also the update rules are exactly the same. So hopefully nothing surprising there. So recall alpha here is the learning rate. So you can kind of think of the learning rate as like the step size of your gradient descent algorithm. And I guess it determines like how aggressively you want to optimize your function. So if your learning rate is big, then I guess each step that you're going to take is also going to be like pretty huge. And so you might be able to like, I guess, find the optimal solution like really quickly, but you might also like overshoot and diverge completely. So yeah. So I guess for last time I said for linear regression, you could either find like you can find the optimal solution by either performing gradient descent or find the closed form solution. So sadly for logistic regression, there is no closed form solution. So And this is true for like most ML models in the real world. So gradient descent here is really your holy grail, which is why we decided to cover it like, I guess, extensively. So the good news is binary cross entropy is convex, just like MSE, at least in the context of logistic regression. So that means our binary cross entropy looks something like this, the function on the left. So in this sense, I guess log loss or binary cross entropy is easy for gradient descent to optimize because there's only one critical point. So you're basically guaranteed to converge to the optimal solution unless you pick a learning rate that is too large. Whereas if we're trying to optimize this function here with gradient descent, then so this function has a lot of like bumps. So what would likely end up happening is you would converge to one of the local minimums instead of like the global minimum. So this is actually like pretty hard for gradient descent to optimize. And in general, there's no guarantee that you would find the optimal solution with gradient descent. And this, I guess the solution that you'll end up with like largely depends on the initial conditions. All right. So any questions about gradient descent? If not, we're gonna go through this fun little demo. All right, so I know we haven't covered neural networks in beginner, but like for those of you who have experience with neural networks, a logistic regression is basically a neural network with no hidden layers. So let me go ahead and remove all the hidden layers. And the activation function that we use is sigmoid. So let me change to that. So yeah, I guess I'm gonna start training. So for logistic regression, the decision, as Nikhil covered earlier, the decision boundary is always gonna be like a straight line, as you can see here. So in this case, it ends up working pretty well because our data is linearly separable. But if we change our data to something else, so this is clearly not linearly separable. So our model is still trying to like, I guess, classify or separate this data with like a line. So this, like, although it's clearly like trying its best, this is not like working pretty well. So if we add a hidden layer, so let's see what happens. So this is no longer logistic regression. This is now like officially a neural network, but let's just look at what the decision boundary looks like. Wait. So now, as you can see, our model is actually learning like a nonlinear decision boundary, which is pretty neat. So it is actually able to perfectly classify this data with like a decision boundary that looks kind of like a circle. So this is why we want to include like the activation function in the first place, or this is one of the reasons, because like what happens if we use like a linear activation function instead to classify this? So if we use a linear activation function, we're still gonna be, I guess, the decision boundary is still gonna be a line because we're removing the only source of nonlinearity from our model, which is the sigmoid function in this case. So what happens if you compose like a line on top of another line? So what you're gonna get is gonna be a line in the end, which is why the decision boundary here is also a line, even though we have like, I guess I could add more like hidden layers just for the sake of demonstration. And okay, I need a bigger learning rate. I guess 0.3, see what happens. I think the learning rate is too big. Okay, anyway, I think you get the idea. So the decision boundary is still going to be a line, even though we have hidden layers. So hopefully that makes sense, or that gives you like another reason why we use like a nonlinear activation function. So that was kind of like, I guess, more advanced, because like this under the context of a neural network and stuff, logistic regression. But yeah, I guess the key takeaway here is like at least for logistic regression, the decision boundary is always going to be like a line. And it kind of like works out if our data is like can be separated by a line, but on data that can't be separated by a line, then we're kind of out of luck with logistic regression. But I think at least for this workshop, we're only going to be looking at like data that can be separated by a line. So that's not an issue. All right. Okay, any questions about the demo that we just went through? I guess if not, let's do a quick poll to make sure like everyone's on the same page. All right, hopefully everyone can see the poll. So the question here is like, which task is logistic regression well suited for? So hopefully this is fairly straightforward. All right, so everyone has answered. All right, so most of you got it right. So the correct answer is B, because the output there is discrete. So, I guess in particular, there's only like two possible outcomes. So either approve or deny. So that is what we covered for, at least for binary classification. So I guess one of you used that facial recognition software, but like, I guess at least for logistic regression, it's not, or the task of facial recognition is like in general, like way too complex for a logistic regression model, as I just kind of demonstrated earlier, because the decision boundary is always going to be a line. So for like effective facial recognition, you would need like a special kind of neural network called a convolutional neural network. And we're going to cover that in a lot more detail in like advanced, I think. All right, cool. Okay, so we just covered binary classification. So let's see what happens if we have more than two classes. All right, so the first problem we have is like, how do we want to label our, I guess, our samples? So imagine we have a bunch of pictures of cats, dogs, chicken, and fish that I want to label. So I guess one possible way to label these data is by assigning like an arbitrary like number to them. So for example, we can assign 0 to cats, 1 to dogs, 2 to chickens, and 3 to fish. So, but like when we're doing this, we're making like an underlying assumption. So namely, like, I guess cats are more similar to dogs than to chicken. Because if you take the difference of a dog and a cat, you get 1. But if you take the difference of a chicken and a cat, you get 2. So I guess in this case, it's actually like I guess the assumption makes sense, because like dogs and cats are both mammals, but the chicken is a bird. So, but in general, this usually like doesn't work out. So we usually want to do like something else. So another way to label our data is by assigning like a 0 to 1 for each category, depending where the image is under that category. So for example, if we have a cat, then if we assume like the first number in this vector corresponds to whether this is a cat, then we want to label it as a 1. And then the rest are just going to be zeros. And then we put these labels into a vector that's indexed by each class. So this process is kind of called like one-hot encoding. So you can think of like, you want to label the, I guess, hot class as a 1 and the rest as zeros. Wait, I guess that sounded a little bit weird. Okay, never mind. So now that our samples have been one-hot encoded, our model needs to have like I guess a similarly shaped output so we can compare like our predictions and our labels when we use our loss function or when we calculate the loss. So yeah, so these are what our images look like now with like, now they're like one-hot encoded. So for a cat is going to be 1000 because the first number here corresponds to a cat. And similarly for a dog, the second number corresponds to where it's a dog. So the one's in the second number. So this actually have an interesting property. So if you take like the dot product between, so these vectors are all orthogonal to each other if they correspond to like different classes. So for example, if you take the dot product of a cat with a dog, you get 0. So that is what I mean by orthogonal. So this actually has some like pretty nice properties, which is like, I guess one of the benefits of using one-hot encoding as opposed to just, I guess, assigning each class like an arbitrary label or arbitrary number as label. Okay. Oh, okay. I was checking chat, but I thought there was a question. All right, so hopefully everyone is good on one-hot encoding. So I guess the takeaway here is like, instead of a number, like everything is now labeled as a vector using like the rules that I just talked about. So recall for binary classification, a single chain example is an n-dimensional vector. So with the assumption that there are n features in that particular sample. And the weight is also an n-dimensional vector. And our bias is a real number or scalar. So for multi-class classification, the input is the same. It's also an n-dimensional vector. Hopefully nothing surprising there. But now our weight is different. So namely, our weight is now an n by c matrix, where n is the number of features and c is the number of classes. So, okay, I can see like a source of confusion here. So the superscript here is actually not an exponent. So it's actually just like an index, I think. But yeah. So I guess you can kind of think of this as like each class having its own weights. And then you're just kind of like combining all the weights into like one huge matrix. So that's why it's n by c. And our bias is also c-dimensional vector. All right, so let's go through the example that we have earlier. So let's say we have an image of a cat. So first we want to take the pixel values from our image, which is like a 2D array, and then we want to flatten it and then put into like a one-dimensional matrix for our X. And then we want to multiply by our weight matrix, or I guess the transpose of our weight matrix, and we want to add to our bias vector. And then we get our prediction. So this is hopefully nothing new. This is like basically what we would do for linear regression as well. And notice how like our prediction here is a matrix with, or a vector of 4 elements, because the underlying assumption is we have 4 classes. I think it was cat, dogs, fish, and chicken. Yeah, so that's the first part. So that was before we apply like the activation function, which we're going to cover in, I guess, the next slide. But first, let's make sure everyone's on the same page. So let me launch this poll. All right, hopefully everyone can see the poll. So this question might be slightly more challenging than the last one, but I think if you look at the slide like earlier, you should be able to figure out what the correct answer is. All right, I'll give it like maybe 30 more seconds. Okay, everyone has voted. So most of you got it right. The correct answer is B. So a reason, I guess let me revisit the slide from earlier. So the reason why this is correct is because, or at least in the context of multi-class, we want our weight matrix to have I guess n by c. So n is the number of features and c is the number of classes. So I think n here is replaced by f. So that might be slightly confusing, but yeah, so basically like each class should have their own like weights, and then you're kind of like combining that into like a matrix instead of like a vector that we have for binary classification. All right, so let's cover the activation function for multi-class classification. So I guess we're using softmax here instead of sigmoid. So let's walk through like how softmax works. So from the previous slide, we have the output vector from our model, which is z here. And then, so the motivation is we want y hat to be like a probability distribution. So y hat should add up, or all the elements in y hat should sum up to 1. So what we're doing here is we're raising e to each of the value in z. And then we're sort of doing this thing where we like normalize this vector. So yeah, we're dividing this by the sum of all the elements in the vector. So this kind of how you would do, or this is like how you would do it when you would try to find like a unit vector, but it's slightly different. Yeah, so I guess like a kind of interesting question is like, why do we have to raise e to the exponent of all the elements here instead of using like a simple ratio? So I guess, yeah, think about negatives. I guess if anyone has any ideas, feel free to share. So Maxwell said e raised to any power never output negative. Yes, that's exactly correct. And the reason why that's important, because like as I said earlier, our prediction or the output vector y hat is like a probability distribution. So if one of the elements is negative, then like you kind of have like a negative probability. So that doesn't really make any sense. Oh, I guess Julian is asking neither was sigmoid though. Why do we use here e here? So actually, I think wait, let me think. Okay, so I guess e is works pretty well like empirically, and as you'll see, like softmax is actually like the generalization for sigmoid. So this whole thing is like a replacement for sigmoid, if that makes sense. I guess like you could also use like any functions that would not output a negative value, but you want this property where like, I guess if the number is like negative, then you want this to be close to 0. And if z is like a big number, then you want the output to also be like a big number. So I guess sigmoid will work, but like it actually like, so basically it'll level off at 1, if that makes sense. So if you have like 1,000 and like 1,000,000, it's gonna be really close to 1. So there's not really any difference. Whereas with softmax, like e to 1,000 versus e to 1,000,000 is like a big difference. Okay, so to summarize what I just covered earlier, so let's say we have our to convert our output z to probabilities. So we first raise e by the components of each of the elements in our z vector. So we get a vector like this, but then obviously this doesn't add up to 1, or this doesn't have to add up to 1. So we do this, I guess we sort of normalize this vector. So we divide by the sum of the previous vector. So now we have like a vector of probabilities, and all the elements have to add up to 1 because we're dividing by this term here. So yeah, this is the final, I guess, output for y hat. Okay, so hopefully that makes sense. So if you have any questions, please let me know. If not, I'm going to move on to the cost function for multi-class classification. So the motivation behind why we need why we don't want to use binary cross-entropy is we need a more general loss function that can apply to arbitrary number of classes, whereas like log loss only works for 2 classes. And I guess we need like a higher cost if our model makes like a bad prediction. So if the image is a cat, but our model predicts that's a dog, we want to have a higher cost than if our model thinks it's a cat. And so the function that we're going to be using here is called cross-entropy, which is short for categorical cross-entropy. So I guess the equation for cross-entropy looks something like this. So this might look like a little bit daunting, but let's unpack this. So recall for so since we're using one-hot encoding, our label here is like a bunch of zeros and ones. So the only class that will contribute to the loss is the class with the 1 in the label, or the class that has a 1 in the label. So the reason why that is the case is because we have I guess we're multiplying the log of y hat by y. So if y is 0, then this whole term is going to be a 0. And if y is 1, then I guess this term is going to be negative log y hat. So in order to minimize the cost, our model needs to make the y hat for that class as close to 1 as possible, because recall log of 1 is 0. So the negative log of something would be close to 0 if that something is close to 1. So I guess what that means in the context of classification is if your model thinks with a very high, or if your model predicts correctly with a high certainty, then the cost is going to be minimal. Whereas if you predict the wrong class with high certainty, then your cost is going to be really high, because like log of something close to 0 is like, or the negative of the log of something close to 0 is like close to infinity. So yeah, hopefully that gives you some intuition of how the cross entropy works. So I think it's pretty similar to log loss, but it's just like a generalization where it applies to like, I guess, C number of classes instead of 2 classes. So I guess the total cost across all training sample here becomes something like this. So we're just taking the per sample cost, which is the L here, and then we're kind of averaging this across all the training samples, and then we get J. So we expand this out, we get like something like this. So I guess don't worry about the subscripts too much if they're confusing. But like, since now you understand like how cross entropy works, then hopefully this should be easy to understand. All right, so let's talk about gradient descent in the context of multi-class classification. So it turns out the derivatives are exactly the same. So that is good news. And the update rules are also exactly the same. So why is this true? Why is this the case intuitively? I guess I gave you the answer. So because softmax is like a generalization for a sigmoid function, you can like try to, I guess, apply softmax to like 2 classes, and you can verify that it is equal to the sigmoid function. And also the cross entropy loss is a generalization of log loss. So that's why like everything works out. All right, so putting it all together. So first we have our image of a cat, which we labeled as 1000. So the first, so I guess the first class is a cat. So that's why I have a 1 here. And then we want to compress or flatten this picture into a 1-dimensional vector, which we can feed into our model. So our model outputs this vector, which has 4 elements because there are 4 possible classes. And then we apply the softmax activation function, and then we get a probability distribution. So in this case, our model thinks with this image is a cat with like a 24% chance, and it thinks this is a dog with like a 64% chance. So I think our model is kind of predicting the wrong thing here, unfortunately. And then we want to feed the output of our model into the loss function along with the label. So this is why we want our model to output like something with the same shape, because we're feeding these 2 like quantities into our loss function, and then it turns out our loss is 2.4. And then we would also like do updates or make updates to our weights and bias, but it is not shown here. All right. So hopefully that makes sense. So let's actually do like another poll. Wait, I didn't stop sharing the last poll. Whoops. Let's launch a new poll just to make sure everyone is on the same page. So the question here is, your model outputs the following probability, but I guess one of the numbers unknown. So what should the unknown number be, I guess? I guess I'll give you guys like 30 more seconds. All right, it looks like everyone has voted. So yeah, everyone got it right. So the correct answer is 1 because there's like a probability distribution. So we want all the elements to add up to 1. So yeah, okay. I think there is actually a question in chat. I think Julian asked, wait, I think this is the question on the last slide. Hold on. So cross-entropy will keep the prediction of dog at 0.64, right? Why don't we try to correct that to 0 as well? So yes. So when we update our weights, we'll try to, I guess, make that probability to be 0. But so our model is predicting like the wrong thing, because this is probably like pretty early in the training routine or the training phase. So our model is still like our model is still learning how to classify all these images. So that's why it's making like wrong predictions like from time to time. So ideally we want the probability to, I guess, resemble the label. So we want the first element to be as close to 1 as possible. So something like 0.99, and then the rest should be like close to 0. So that would give you like the minimum loss. So yeah, hopefully that makes sense. So this example is not reflecting like the best possible, I guess, performance on our model, but is this just like an example of how like our, oh, I thought cross-entropy will only update the first element. Okay, so that's only for the loss. So the gradients update rules are, so gradients here is actually like a completely like different thing. So this would give you like a vector with probably like, usually it's all the elements are going to be non-zero, and then you use this update rule. So I think I said earlier that yeah, the loss would only, or the second class would contribute to the loss, but the gradient is different. So the computation is different. And yeah, again, this is shown like matrix form, so it could be a little bit more difficult to understand, but yeah, basically if you predict the wrong class, it's not going to be, so it's not going to be 0. All right. Hopefully that answered your question. If there are no further questions, let's jump into the coding exercise, which is quite a bit shorter than the one last time because I think this is a pretty long workshop. So yeah, let's go ahead and wait. That's not what I meant to do. Okay, so I was gonna save a copy in Drive. All right, so I'll give you guys maybe like a minute to save a copy in your Drive. I just let me know if you're done. All right, so let's first import all the modules. So yeah, we're gonna be working with the iris dataset again. I guess let's look at the documentation first. All right, so I guess we already used this function like in our can workshop, but so what the load iris function do is it returns the iris data set. So the return type is, I guess, an object of the bunch class, but unless return xy is set to true, in which case they will just return the data and the target in like a tuple. So this is like relatively new. So yeah, that is what we're going to be doing. So we want to load the iris data set, but then this time we want to store in like a tuple instead of like an object. So load iris, turn xy is true. So now let's print out the shape. So x is our data. So the shape is 150 by 4, and y is our label, so it's 150. So there are 150 samples and 4 features. And now let's drop the last 2 features because we'll just work in 2D for now. So x now has a shape 150 by 2. And then, yeah, let's tackle binary classification first. So I think I have defined a function that converts the data into like a binary, or yeah, into like binary class. So I think I use some like NumPy data slicing. So we'll teach you how to do that in the next workshop. So don't worry too much about it. So what I'm basically doing here is I'm just figuring out like which elements in the data has like class does not have class 2, and then just remove all the elements of class 2. All right, so I guess now it's like when the coding actually starts. So I want you guys to try to call the function that I just defined on x and y, which is our data. So maybe I'll give you guys like a minute to, or 30 seconds to figure out what this should be. All right, so Maxwell said convert to binary x comma y. So yes, that is correct. Let me copy that. And let's print out the shape. So there are like 50 samples that is of like, I guess, the 3rd class. So now our data only has like 100 samples. So I guess like, okay, never mind. Okay, so next we're gonna do some like visualization. So I think I defined a function for you where we plot the data in like I guess in 2D. So what I'm doing here is I'm basically like separating the data by which class they are in, and then I'm plotting them like separately. So yeah, in the interest of time, I have already done this for you guys. So your job here is just to call this function on the data that we got. So x bin and y bin. So yeah, I'll give you guys like maybe 30 seconds again. So this should only take a line. All right, anyone has any ideas? All right, so as I said earlier, we want to call plot data on X bin and Y bin. Oh wait, there is something in the chat. Yes, so yeah, that's basically what I just said. So now you get this nice little plot where it basically, like, I guess, plot the data depending on which class they are in. And so the goal here for our model is to learn a line that separates these two classes, or data from these two classes rather. So it looks like this can actually be done with like so it looks like the data here is linearly separable. So hopefully that's the case, but I guess we'll find out soon enough. So the next step here is to split our data into like a training and testing set. So I think, yeah, we're supposed to be using train test split. So here's the documentation. So hopefully you guys still remember how train test split works. All right, so Maxwell said train test split X bin, Y bin. So yes. So those are the first two arguments. But then we also have, like, I guess, a few more arguments that we want to pass in. So yeah, like I said, like the first two arguments should be arrays. And then we also have like the test size or train size. So these are complementary. So you can, I guess, pass in like one of them and the other can be determined. And then we also have like the random state, which determines like how the data is split. And the shuffle parameter here like determines like whether the data are shuffled. So default value is true. So in general, you want this to be true. So I think Nikhil actually like demonstrated this like earlier or in the last workshop. So I'm not gonna cover like too much about like why we should shuffle our data. And then the return value is a list with 2 times the length of our, I guess, our input array. So because our input has like 2 elements, or yeah, our input is like an array of 2 elements, and then so our output has 4 elements. All right, so any idea what the next 2 arguments should be? Yeah, I guess the hint here is to leave shuffle alone because it's already, so it's default to be true, so you don't really want to mess with that. And then I guess stratify is like more complicated, so we also don't really want to mess with that either. Okay, so we want to set our test size to maybe like 0.2. So that means like 20% of our data is going to be the test data and 80% is going to be the trained data. And then I guess we can just set the random state to something arbitrary. I guess maybe like 9. All right, so now we have our training and testing data. So the next step here is to actually like define our model or initialize our model. So let me open the documentation. So let's see, there's something in the chat. All right, Maxwell said logistic regression dot fit extreme watching. So yes, that's correct. All right, so maybe let me cover the documentation a little bit, even though it's actually the same as the linear regression or KNN. So the beauty of scikit-learn is like the API for all the models are basically the same. So for those of you who don't remember our, wait, where are the methods? All right, All right, so these are the methods. So the really important methods here is fit. So fit basically fit the model according to the given training data. And then predict, basically predict or makes a prediction on the samples. And then we also have the predict log probabilities, which actually gives you like a, I guess, a probability distribution instead of like a ones and zeros. And then the score here returns the mean accuracy of the given data. So these are really like the most important methods. And then, so yeah. So one thing to note here is fit actually returns an instance of the model or a reference to a model. So that's why you can create the model and then call fit immediately and then take whatever fit returns and then store it in our variable. So let's run this. All right, so now let's compute the accuracy on our test data. So I think I just shown you like all the methods that you have to know. So yeah. So these are all the options we have. So I guess I'll give you guys like a minute to figure out like which method we should call to get the accuracy. All right, so Maxwell said score x test y test. So that is correct because like I said earlier, score returns the mean accuracy. So in this case, our accuracy is 0.95. So I guess it's pretty good, but there's like one outlier that our data is not able to classify correctly, which is kind of unfortunate. All right, so I guess like, okay, let's cover the attributes. All right, so the model has like a bunch of attributes that you can access. So the really important one here is like the coefficients. So this is our weights. And then the intercepts here is our bias. And then there are also like, I guess, some other attributes which determines like how many classes and the number of iterations. So yeah, so which attributes gives you the weight of the model? So this is important for, I guess, for the plotting in the next step here, but this is just to test where like you've been paying attention. So there are only 4 options, as I said earlier. Okay, yeah, so dot coef would give you the weights. So something to note here is there's like an underscore at the end. So yeah, this is what our weights looks like. And then we can get the bias by getting the intercept. Oh, what am I doing? All right, so in the next cell here, we want to like sort of plot the decision boundary just for like visualization purposes. So here I'm trying to like calculate the slope and their intercept for this particular line. So this is a little bit like tricky, or it's not tricky, but like it takes like a little bit, it takes you like a minute to like figure this out. So I've done this for you already. So your job here is to plot this particular line with Plt Dot Plot. So I guess for those of you who are not familiar with matplotlib, so let's look at the plot function here. So plot takes in, well, x and y, and then there are also like a bunch of optional arguments, which we're going to cover in a minute. Okay, so Maxwell said Plt Dot Plot x plot comma y plot. So that is exactly correct. So this is like the basic way to call Plt plot. You can also like pass in some other arguments. So for example, you can set the color, and you can also label this. Just call it decision boundary. All right, so when we run this cell, we get this nice little plot. So Plt legends will give you like a legend here, which is pretty nice. So yeah. So actually, like I think this data set can be separated by, I guess, a line, but like it looks like this sample here is being like misclassified. So like this, the outlier down here. So that's kind of unfortunate, but I think our overall model is doing a pretty good job. So yeah, I think we'll cover more about logistic or multi-class logistic regression in one of our guided projects. But yeah, in the interest of time, this is the end of the coding part. So hopefully this is I guess not too confusing. So yeah, this is the end of the workshop. Thank you for coming. If you have any questions, you can stick around, and please fill out a feedback form here. So yeah, we always look at our feedback forms and we try to like make some adjustments, which is why I guess the coding becomes like a little bit easier. And so yeah, next time we'll cover Numpy and Pandas, which is like two of the most popular like machine learning and data science libraries in Python. So these are going to be important for our guided projects. And yeah, also check out our Facebook and GitHub. And I guess the meme for a day is Grumpy Pandas more like Numpy and Pandas. Am I right? That was a little bit lame, but yeah. All right. Yeah, I guess if you guys have any questions, feel free to stick around. I'm gonna stop the recording.
Yeah, too.